Hi, everybody. We're going to go over some fundamentals about capacitors in this video. We're just going to sort of introduce them and get an idea of what a capacitor is, what its units are, some various types of capacitors, and also how they sort of function when they're in series or in parallel. So, first of all, what is a capacitor? In essence, or sort of the first thing about it is a device component that can store energy. That's its main, not its main purpose, but one of its main attributes or features of a capacitor. Physically, this is pretty much true about any type of capacitor we're going to talk about. Exactly what the metal is made out of and what the material in between the metals is made out of varies. But essentially, physically, a capacitor is two metal plates separated by a material we call a dielectric. So it has some sort of electromagnetic properties and kind of acts like an insulator to keep the two metals apart from touching, right? So in essence, what you have is metal plate, and then some sort of dielectric. Exactly what the dielectric is way beyond anything we want to talk about. What it does in the electromagnetic range, we don't care at all. But fundamentally, it's two plates, and when we apply a voltage on that, what it does is it forces the electrons off one plate to move to the other, so that one side becomes more positive and the other side becomes more negative. Okay, so you would never do this necessarily straight to a power supply. Okay, so this is your capacitor. And this is a voltage of whatever, it doesn't matter. And so this is the higher potential, lower potential. What this does is it attracts electrons and makes them go all the way around and build up here. So we know that we learned that it's the electrons that move, not the protons, not the positives. But as you remove negatives off this plate, electrons off this plate becomes more positive. So that you have a potential difference. Remember that term, right? Potential difference between the two plates that will be eventually equal to this voltage that we have here, right? So that's fundamentally what a capacitor does. Now we can define capacitance as the amount of charge a capacitor can hold or store per volt, right? So we use the letter C for capacitance. Equals Q, which is for charge. If you guys remember that, a long time ago, we mentioned charge when we were talking about voltage and current over V, all right? And charge is measured in coulombs, and voltage is measured in volts. And so capacitance, we define it, is measured in something called farads, F-A-R-A-D-S, farads, or F. We use the letter F. Okay, and farads is just coulombs over volts. Again, not something you have to memorize. You do need to know capacitance is measured in farads. You do need to know that capacitance is how much charge it can hold per voltage, per volt. Okay, so you need to know that farads is a measure of how much charge can be stored on this capacitor. So obviously the bigger the number is in farads, so the bigger the capacitor is in terms of a value, the more charge it can hold, which is, it lends to reason that that is the case. All right. We're not really going to worry about a ton of other details about how the capacitance is handled and all this stuff. We just need to know that capacitors have a capacitance. A couple of other terms that are good to remember and to know. Okay, though again, we're not going to go into a ton of detail of these, but just keep them in the back of your mind, because usually most capacitors have something known as a voltage rating. Okay, it's often written on the capacitor along with the capacitance in farads. So you have a voltage rating, or also known as the breakdown voltage. And this is really a property of the dielectric, the material you have between the plates. And it's essentially how much voltage you can put across two plates before it's too strong and actually arcs over, so it's no longer an insulator, right? So you can actually put so much voltage on a capacitor that it breaks through that material and you arc over, and your electrons actually get to the positive plate through the dielectric rather than going through the circuit. Okay, so it's just a term, voltage rating, just so that you're aware of it. No, I'm never really going to ask that question. It's, but it's something important as you start dealing with capacitors. All right. There's another thing about what we call leakage, and this is usually refers to a leakage voltage. So even though capacitors are meant to store voltage, store energy, store charge, it is possible, and there is a certain parameter or characteristic of a capacitor that allows, bad choice of word, but that some voltage does leak out and you slowly lose some charge on a capacitor. Again, just more to keep it in mind, nothing really to write about or anything. Now, if we talk about the types of capacitors, and I mean, there's tons of different types of capacitors, but I'm just going to mention 4 of them. So the first one is called a mica capacitor. And it's called this because the dielectric is made of mica, which is a material. Okay, yeah, it's a physical material called mica. Sorry about that. Got my pen too close to my tablet. These are often used in RF applications because they have good properties in higher frequencies. Okay, so just to be aware, again, there's still 2 plates, metal plates, but with mica in the middle. And if I were to show a quick picture of this, the one we're going to see is not it, just right here. So this is typical what it looks like. I mean, they can look different, but this is sort of a typical, they've got this kind of rounded, squared, rectangular shape, and they're normally often this color, all right? So that's your mica capacitor. The other one that we also talk about is the ceramic And you guessed it, the dielectric is made of ceramic. And these are super cheap. Well, I'll call it in quotations cheap. Okay. Just they're the most prolific, usable in many applications. Mostly low frequency. Now, we're not going to go into frequency and all this stuff in this semester. That's for AC circuits next semester. But just know that frequency, RF applications is very high frequency. So that's why you need the mica capacitor. Ceramic capacitor is really only good at lower frequencies. Okay. But they're super cheap. They're easy to use. They're like, doesn't matter which way you put them in, just like a resistor. Okay. Another type is a plastic film or just film capacitor. All right, and you guessed it, the dielectric is made of a certain type of plastic, and there's different types of plastic that you can use. All right, so dielectric is a plastic, all right, from, I don't even want to go through them, like polyurethane, whatever. There's just a whole lot of different plastics, and they kind of fall in between the ceramic and mica. Okay, they got some good properties, low dissipation, meaning they kind of slowly dissipate their charge. It's not a quick dissipation. So they kind of fall in between the two, right? And the third one, the last one, sorry, is called an electrolytic capacitor. And it uses an electrolyte essentially and some other things. It's a complex way of how they set it up, but this is essentially the main capacitor that is polarized, meaning it has a plus and a minus side. So how you put this in, you put it into a circuit is extremely important. All right. So this one we can't put in backwards and hope everything's okay, because it won't be. All right. So they will pop, they will blow. They're not a joke. When they get put in the wrong way, it's almost like a gunshot and will scare the bejesus out of you. All right. So you don't want to play with electrolytic capacitors. Just to sort of show that all the capacitors, what they kind of look like. I kind of skipped that quickly, but so there's the ceramic. Here's what sorry, that was the mica. Here's the ceramic ones. Very generic. Sometimes they look like little squares. Sometimes they got these little legs. Sometimes little circles. Very generic looking. This is going to be the majority of the ones that you're going to see, at least in most of our courses. Then we have the plastic film ones, and they come in all sorts of different shapes and sizes, as you can see. The one that we'll see most often is like this, where the legs are off on the ends. This is what we call an axial capacitor or an axial component, where the legs come out the end, just like a resistor. Resistor is an axial component as well. All right. And then the electrolytic ones look like this, and they all have like a sort of a darker line where they either show the plus or the minus, it depends. And it points to which leg is the positive and which one is the negative. All right. You'll also notice, you can kind of see here, right? This one's 25 volts, 100 microfarads. So 25 volts tells me that's the max I can put across this. That's the breakdown voltage. Same thing over here on this orange one. If you can see, it's 50 volts and 47 microfarads. So 47 microfarads is the capacitance, and sort of the breakdown voltage, the max it can take is 50. All right. So that's really all I want to say about the types. Next, I want to look at what happens when capacitors are in series with one another. So just like we can put resistors in series, we can put capacitors in series. And really, fundamentally, this is all I want you to remember, okay? So we got a bunch of capacitors, to whatever, you know, I'll call this Cn to be whatever, meaning how many we have, C2, C3, C4. And how they add up is just like resistors in parallel. So you actually do a 1 over Ct equals the 1 over C1 plus 1 over C2 plus blah, 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 however many you have, up to 1 over Cn. So Ct will be all that, or C total, to the minus 1, all right? So even though they're in series, they kind of add up like parallel resistors. Not going to go into the math of why it's like this. If you're really super interested, I mean, there's websites that'll go into the details of why. You need to go a bit into the calculus to really fully get the idea, but that's why I don't want to touch it. We just need to know that that's what it is, all right? So if I have two capacitors in series and I want to find their total capacitance, I have to do this kind of relationship. So I think you can kind of guess, you know, what happens when capacitors are in parallel. So it's the opposite, right? So when I have capacitors like this, they're actually going to add up like resistors in series, okay? However many, up to the Cn again, however many that is, C1, C2, C3. So C total would just add them up, C1 plus C2 plus however many you have up to the last one, okay? So keep that in mind. This is important because we can sometimes want to put two capacitors in parallel or two capacitors in series, or we don't have an exact value. So we use two capacitors to try to get the exact value that we want or close to it. So you have to know, do I put it in series? Do I put it in parallel? Right? So just remember, capacitors function in the opposite way of resistors. So capacitors in parallel, we add them up like this, the 1 over type of summation, like resistors in parallel. And then capacitors in parallel just simply get summed up, just like resistors in series. So they're the opposite of each other in that perspective. And I'm going to stop here for this video. I hope it was helpful, and we'll talk about how capacitors function in DC in the next one.